So I'm going to talk about interventions, causality, quantum correlations, that are things that have been the focus of most of my work in the last years. So yeah, let's start with something that seems to have little to do with quantum foundations, that's ice cream. A quick search in the internet, like we can plot as a function of time, as a function of the different seasons of the year, like ice cream sales and production, consumption. And compare it with other variables like shark attacks, violent crimes, forest fires, drowning deaths, and many others. And we see a clear correlation among these. This seems funny at first. So is ice cream such a terrible villain? And of course, we know what's going on here, as the statisticians would never let us forget, correlation is not causation. So what's happening here, we can clearly see like this peak around the summertime in the north part of the globe, is that the sunny hot weather is the common cause between, like, let's say, ice cream increased consumption and sunburn and all these other tragedies that we mentioned. So in hindsight, this is almost trivial, right? Like, correlation is not causation. This is the mantra of statistics. But I think this has gone too far, and this is well exemplified by this article in Wired magazine some years ago, where the author says something like, correlation supersedes causation. Science can advance without coherent models, unified theories, anything at all. Correlation is enough. Just throw the numbers in the biggest computing centers we have, and let the algorithms find patterns where science cannot. This would be very bad news for us as a scientist, but lucky us, nothing could be further from the truth. And a good example of that is this paper by Kalud and Longo, where they basically take many different kinds of large database, and they show that they tend to contain arbitrary correlations that appear only due to size and not the nature of the data. So if we just take a mountain of data, we are always going to find something. In the sense that most correlations, they are then spurious, like too much information. I like very much this message that they convey in the paper tends to behave like very little information. A funny example of that, like we can, with modern machine learning algorithms, we can easily recognize chihuahuas or these ringlet dogs, but we can also easily confuse the machine by throwing some arbitrary correlations in the data, like these muffins or these towels. And I think the point here is that if we look enough, we are always going to find patterns where there is only noise. So data cannot be interpreted in a theoretical vacuum. Typically, we start from a hypothesis, and only then we perform an experiment. We don't perform random experiments, and then we try to find something with data. But there is a crucial problem here, because if correlation is not causation, and as the statisticians would say, we can only infer correlation from empirical data, then where should we start from? Like, we have to start with a hypothesis, but if we cannot really get that from data, then it's a kind of a circular argument. We don't know where to start or where to stop. And I would say that exactly to solve this very fundamental problem, that the causality theory has been invented. So that's kind of the things that we are going to talk about today. And here is the outline. So I will start a bit like with causality theory. You can understand that as a kind of crash course on causality theory. Then we are going to move forward and see how indeed we can distinguish correlation from causation using these interventions. Then go one step beyond and talk about something that allows us from simple observations. We don't need to intervene, actually. We can also distinguish correlation from causation. So this is like a very robust and nice causal framework. But then we are going to mess things up by throwing correlations in the picture. And then we are going to see that we have to change some of the fundamental assumptions we have in the classical theory of causality. So let's start with causality theory. In the mid-90s, like Pearl, that's one of the founding fathers of this field, and of course many others, they realized that to teach their machines, they would need to go beyond correlations, like beyond simply recognizing patterns. So the machines, to really learn, they would need to like also be able to recognize from empirical data patterns of cause and effect relations. So how can we do that? So let's go back a bit in time. like 50s, 60s, I'm not sure, like when Hans Reichenbach in one of his books stated this principle that goes against the mantra of statistics and basically says, well, there is no correlation without causation. In the sense that if an improbable coincidence has occurred, there must exist some common cause and or a direct causal influence between these two apparently coincident events. So let me give an example. It's bad luck that I'm not in Vienna, but if I would be there, like let's say before the talks would start, I would arrive, grab a coffee and sit somewhere in the institute, and I would be looking at two rooms. And every time I would do that, I would see that the lights in these two rooms would be either off or on, off, on, off, on. So it's like a correlation, a perfect correlation in this case. And it seems very unlikely that every time I'm sitting there looking, like random people would at the same time enter and turn on or off these light bulbs. So Reichenbach would say, well, there is some sort of causation. The question is which kind? Could be some bad wiring in the walls that, like, whenever I turn on or off one of the light bulbs, this causes the other light bulb to also be off or on, or vice versa. Or could be that the wirings are fine, and actually what's going on is that there is a third event that I might not directly observe, so I have to treat this potential third event as a latent factor, as a hidden variable, if you wish. That it's the common cause between these correlations. So it could be like some short circuit happening somewhere outside the building, or could be something more mundane, in the sense that, like, these two rooms that I'm looking, there are classrooms, and in Vienna, the classes, they always start and end at the same time. So this would explain these correlations that I see. So that's very simple, but it's the basic setup we have in causing theory. So we have empirical data, lights that are on or off. We might have some potential latent factors, and from that, and from what we observe, we want to infer cause and effect relations, like these arrows here between these variables. And of course, this fits very well in machine learning, like our artificial intelligence setup. We can imagine like a machine that has sensors, is able to sense the world and observe and like interact with this world. And from these interactions, is able to learn something, right? Learning here, it's not only drawing correlations between variables, but it's really like learning what is causing what. So how can we do that? The first thing is that we have to encode these causal relationships, like the causal structure that we are trying to test, in what we call a directed acyclic graph, a DAG for short, where each node in this DAG stands for a variable that it's important in our model. And these directed edges, they encode the causal relationships between the variables. And the important thing here is that the causal relationships, they are encoded in the conditional independencies, the CIs that are implied by the DAG. So what I mean with that? So let's look here. This is the triangle that Nicolas Brunet have talked about, and that many people in the audience, I'm sure they like this. These two variables, lambda1 and lambda2, I do not have an arrow from one to the other, nor there is a third variable that acts as a common cause between them. So these two variables, they should be statistically and causally independent. In terms of the probability distribution that this model generates, of course, like I have this sort of independence relation here. Another one is like A and B. They are correlated because they have a common ancestor, lambda1, but these correlations should be screened off if I condition on this common ancestor. So I have like algorithms that are able to, given some DAG, given some causal structure, to basically list all these conditional independencies that, again, importantly, they encode the causal relationships about my model. So let's see how I can use that in practice. Let's say that I did some experiment like involving these 6 variables, and from this data, I can construct some probability distribution. And then I have some hypotheses. Like I'm not going to talk here about how I get to this hypothesis, but this causal inference can also allow me to do that. But let's say that I have these hypotheses, and I want to falsify or to conclude that indeed this causal hypothesis is compatible with my data. So how I do that? I basically take my empirical data in the form of a probability distribution, and I check if all the conditional independencies implied by this model are satisfied or not. If one of them fails, then I can be sure that my hypothesis was false. Like I cannot use it to explain the data that I'm observing. This seems very good, but the problem is that in practice, we never have access to all the variables that compose a given causal model. We always have some latent factors that we cannot exclude. And the most famous example that we would know is like Bell's theorem. I'm not going to enter in all the details here, but basically we are imposing a given causal structure to our quantum experiment, where we have two very distant labs and a source in between them that I'm representing here by this lambda. The source sends these physical systems to Alice and Bob. They choose what to measure by flipping a coin, these variables X and Y, and depending on that, they make a measurement and get outcomes A and B. And the point here is that we don't want to assume to have access to all the degrees of freedom of the source, because in the end of the day, we don't have really direct empirical access to it. We are measuring it and getting some partial information about that. So we cannot be sure that, let's say, the wave function has a full description of all degrees of freedom of our system. So we have to trace out this lambda from our description. And then what we work with, it's like this observed probability distributions, P of AB, the correlations between Alice and Bob, given that they chose to measure something. And the problem here is that most of the CIs that, again, encode the causal relations, they happen to be in the space that involves this variable that I don't have empirical access to. So like the first one is this, that we can call that a free will, that Alice and Bob, they can choose what to measure, like independently of how the system is being prepared, because the two labs, they are very far away. Whatever Bob is doing in his system cannot affect what Alice is seeing, and many others. But the crucial point here, as realized by Bell and by this community in causal inference, is that constraints on the level of things that we do not observe, they also imply constraints on the level of things that we do observe. And we would call that Bell inequalities. So in a sense, like Bell inequalities are nothing else than these constraints that arise from imposing a classical causal description to a given experiment. Great, so it seems that we have solved the problem. Using this very simple, nice framework, we can, in principle, ask and solve any causal question, right? Like I have some data, what can I conclude from the causal relations among these variables? So let's try to use that in the simplest possible causal question that we can do is like, if I have two observables, A and B, two variables A and B that I see they are correlated, can I use this nice framework to say that A is the cause of B, or if there is some common cause among them? And we are going to see that in general, we cannot do that. So we have to introduce this notion of interventions. So that's the question. A and B, they are correlated. Is this because A is a cause of B, or there is some perhaps not observable variable that acts as the common cause among those? And like this very famous question, does smoke cause cancer? We see a very clear correlation between these variables. People that smoke, they have a higher chance of developing some disease. But as the industry, like many years ago, would say, well, but this is not, as the statisticians would say, this is not a proof of nothing, because it could be that there is a third node, let's say TV, that that's making people more likely to smoke and at the same time to develop cancer. In to which sense? Like in the 50s, 60s, we would see this kind of advertising TV, like saying that doctors love to smoke, or like it's very cool to be like a Marlboro man. So people would have a higher chance to become smokers. But at the same time, because like this was a new technology, maybe like this radiation here would be causing some mutations, and this would make people develop cancer. It's not because people are smoking that this cancer is developed. So how can I distinguish between this error and this common cause? And in this very simple example, I cannot, simply because it's too simple. Like these two causal structures, they are indistinguishable, in the sense that if I try to derive a Bell inequalities for these things, like there are going to be no non-trivial Bell inequalities. So I cannot really distinguish these two things. Okay, so then this framework that I had before seems to be not so good. So I have to introduce something new. And this something new, it's what we call intervention. In the sense, so now the model we have, it's something like this. I have correlations between A and B, and this arrow, this direct causal influence could be there, but like this common cause could also be there. And I want to somehow quantify what's the weight of this arrow here between A and B. And to do that, I intervene in my system, that it's denoted here by this doing A, forcing A to assume a value that it's under my control, and it's independent of the rest of the universe. So if I force A to assume a value, in practice, what I'm doing, I'm erasing all the incoming edges that come to A. In particular, this potential edge that comes from this potential common cause. And if I still, after doing this intervention, observe correlations between A and B, then now I can be sure that these correlations are due to this causal error here, because this error is not there anymore. The point is that observational data, it's different from interventional data. And this also allows us to introduce a very simple measure of causality, that it's what we call average causal effect. It's what we are going to focus in the remaining of the paper, that basically quantifies how much the probability of B shifts if I force A to assume a value A or A prime. So how much B is listening to A. Very nice. So like in principle, I can use these interventions not only to identify these direct causal influences, but also to quantify that. The problem here is that interventions are not always possible. I mean, I cannot take a group of people, put them in a cage, and force them to smoke like 2 packs of Marlboro for many years and see if they are going to develop cancer later or not. So the basic question remains is, can we infer causality from observational data? And the answer is yes, and it's given by this so-called instrumental variable. So what I have here, it's basically what I had before. As I observe some correlations between A and B. This might be due to this common cause or to some direct causal influence from A into B. Now I put a new variable in this system, that it's the instrumental variable X. And this instrumental variable has some causal influence over A, but not directly over B, and it's assumed to be independent of any potential common causes that might affect A and B at the same time. So what this means is like my variable A now, she's still listening to the variable lambda, but now she's also listening to a new variable. So it's like instead of forcing people to smoke, I'm a government and I can increase or decrease the taxation on tobacco. If I decrease too much, more people are going to start to smoke, and they might smoke more because it's too cheap. And if this causal error is really there, then I should see this increase in the number of smokers should be reflected in an increase in the number of people that develop some kind of disease, and vice versa. So you see, by simply doing this, introducing this extra variable like taxation on tobacco, I can in principle infer the causal relation between A and B. And how can I do that in practice? Well, as proven in this very fundamental paper from Pearl and one of his students, we can use this observational data. I'm not doing interventions anymore. It's like I'm looking to the correlations of A and B, given that I taxed more or less the tobacco. So looking at this observational data, I can put lower bounds on the amount of causation that I have in this system. So the message here is that using observational data, I can infer what would have happened if I would do intervention. I can infer what would have happened if I put a group of people in a cage and I forced them to smoke. So for me, this is like a very nice counterfactual kind of argument. We don't need to do something in order to know what would have happened. Okay, but there is still one problem here, is the fact that how can we know that we have a good instrument? And what I mean with that, for these bounds here to be valid, I have to be sure that my causal assumptions are being fulfilled in my experiment, in the sense that like this variable X cannot have some direct causal effect over B, nor it can have some correlations with this variable lambda, that it's the common cause between A and B. Because if this happens, these bounds are not valid anymore. And to solve that, Pearl, he basically derived his Bell theorem for cause inference. He realized that, like, independently of Bell, I really don't think that he knew about the works of Bell, that this when we impose a given causal structure to an experiment, a classical, like, of course, everything we are talking so far is classical, like that this causal model will imply some constraints on the level of things that we observe. So these instrumental inequalities mean that if I violate one of them, and here's just one example of how these inequalities they look like. If I violate one of them, then I can be sure that I have a bad instrument and that these bounds, they don't apply anymore. So that somehow, for reasons that I don't know well, like either X has some influence over B, or like has some correlations with this variable lambda. So this is very nice, like and this is really like a framework that it's used in a variety of fields, like basically in any field where we want to know some causal influence of a variable in another one. So basically in any field of science, like from observational data, I can estimate causal influences like interventional data. And indeed, I can know for sure that I have a good instrument or not, by doing this sanity check if my instrumental inequalities are violated or not. Okay, so this is all very nice. And then when I read about this for the first time, I think it was in the blog of Michael Nielsen. I'm not sure now, but I said, okay, like this is all very nice, but it's classical. And since Bell's theorem, we know that quantum predictions are incompatible with most basic notions of cause and effect. So the first question it came to our minds is like, can we really shake these pillars with quantum mechanics? And that's what we are going to do in the second half of the talk about like how quantum correlations change our view of this framework that I have just described. Okay. The first thing we can ask, it's something very similar to what Bell did, like more than 50 years ago. So Bell, from a causal perspective, it's like this. We are imposing a causal structure to a quantum experiment and asking whether a classical description of this causal model can explain the data that we observe. And the answer is no. So we can make the same question to virtually any causal structure. So the point now is that we are going to impose this causal structure to a quantum experiment and ask whether a classical description of it's able to explain the quantum data or not. And the answer is no. And the simplest case where this works, it's the case where Alice and Bob, they have binary variables, and X assumes at least three values, so like X1, X2, and X3. A classical description would be given by some hidden variable model of this kind that follows from what we call the Markov condition of the DAG. And it implies instrumental inequality, we can call that a Bell inequality too, of this form here. So here's just the expectation value of what Bob is observing, of what Alice is observing, and the expectation values between their correlations. And in a classical description, this should be smaller than 3. Can we violate that with quantum mechanics? And there are different ways that we can quantize this causal model here. The one I'm going to talk about is simply to replace this classical source of correlations by entangled state. And if we do that, we see that we can violate this bound reaching 3.82. So let me speak a little bit about what is this quantum causal model. Now we have entangled state between Alice and Bob. Alice, she's going to decide which kind of measurement she's going to perform, listening to the instrumental variable. And Bob, in its turn, like he doesn't have, he has not a freedom of choice. He has to measure in his system what Alice's outcome is telling him to do. So now his measurement depends on Alice. So we see here a very clear difference with the Bell scenario. Like Bell scenario, we have freedom of choice for both parties. And more than that, like they are spatially separated. And here we have a temporal scenario. First Alice, then Bob. Okay, so we can violate, this is nice. I mean, it's very simple, but it shows that like we can extend this notion of non-classicality, of this incompatibility of quantum with causal predictions to other causal structures that are fundamentally different, I would say, from Bell. And from the causal perspective, this is also nice because it shows us that we have to reinterpret what the violation of instrumental inequality means if we have quantum effects that are present. Because in a classical setting, we can prove that like a violation of this would mean that one of my causal assumptions is being violated. Like for instance, I think that my variable x has no direct causal influence over b, but if I violate this inequality, actually I have, and I can quantify that. So like it's a causal interpretation for the violation of this inequality. The more I violate it, the more should be this causal influence from x into b. But if quantum effects are present, this changes because, well, I'm imposing the instrumental causal structure to my experiment. So actually what I'm proving is that I have non-classical effects present in the mechanisms that are generating the data. Okay, and we can also make a more detailed comparison between instrumental and Bell. And it's this, right? Like Bell, we have 5 variables. Here we only have 4, and Bob has this freedom of choice. Like they are spatially separated, and here they are temporally separated. But if we look a bit closer, we see that actually we can map one model into the other, because like we can see the instrumental scenario as actually a Bell scenario, where the choice of Bob depends on what Alice is obtaining in her lab. And if in a classical model, if A depends on lambda, so this means that that the choice of Bob also depends on this lambda. So actually, we can interpret this as a non-local hidden variable model with measurement dependence. But this is nice because it's showing us that if I make a standard Bell experiment, like Alice and Bob, they measure locally, and if I violate instrumental inequality, then what I'm proving, it's a stronger form of non-classicality as compared to Bell, because I'm showing that the correlations that I'm generating locally in my system, they are actually incompatible even with a classical non-local hidden variable model of this form. Okay, so it's like I would say this is a stronger form of non-classicality as compared to Bell. Okay, nice. So we know that with Bell correlations, we have a lot of applications in this device-independent setting, like communication complexity problems, randomness, self-testing. So the next question that we asked ourselves was like, can I use this violation of these instrumental inequalities, for instance, to generate and certify randomness? So here I have the usual setup. I have some initial seed of randomness. I put this into my instrumental causal structure. I generate some outcomes for Alice and Bob. Now I use some randomness X factor, and hopefully from that I get some secure quantum bits, in the sense that they are independent of the rest of the universe, like in the sense that they're truly random. So our aim here was to try to compare what we can get from an instrumental scenario from differently from a Bell scenario. We are not reinventing the wheel here. We are just looking at using the standard tools and looking at the standard benchmarks, like this age mean, that is basically quantifying how random or how independent are the outcomes of Alice and Bob from the outcomes of some potential eavesdropper that it's listening here in the line. And if we plot this mean entropy as a function of the visibility of the state that we are using here to violate the instrumental inequality, we see in red what we get with Bell, and in blue what we get with the instrumental. So for visibilities 1, they are the same, but it seems that the instrumental is worse than Bell for lower visibilities. Okay, so too bad. It seems that even though this has an application, it's not better from what was known before. But actually, that's not true, because to compare these two curves, what we should do actually is to compare how much randomness we put in from how much randomness we take out. And then here, in this case, in this fair comparison, we have the hope to indeed have some benefits from the instrumental case. Why? Because here in Bell, I have two, like in the CHSH case, I have 2 input bits. I have one for Alice and one for Bob. And here in the instrumental, I have only 1 input treat for Alice. Bob, he has no randomness. He's doing what Alice is telling him to do. So if we do that, we see that indeed we can have some advantages. So here I'm plotting the bit gain. That means like how much bits I put in, how many bits I get out. And I'm plotting here the bit gain for the instrumental case divided by the bit gain for the CHSH case. So whenever this is larger than 1, these curves are larger than 1, I get like an advantage from the instrumental scenario. And we see that indeed we get that for regions of very high visibility. Okay, so not only we can do it, but we can get some advantage from what was known before by using this new causal structure. So in the last part, let me change gears a little bit and talk about something that I think it's much more fundamental. In the simplest instrumental scenario, where all these variables here are dichotomic, it's known from this paper by Hanson, Law, and Pusey from 2014 that all the correlations are classical, in the sense that even if I have quantum or post-quantum correlations here, I can never violate the instrumental inequalities for this kind of scenario. So it means that like this quantum description in terms of the Born's rule, actually I can decompose in terms of a classical description. Very nice, but this happens for the correlational level. This doesn't say anything about the interventional level of my experiment. So the question we had here was, well, what about interventional data? I can have this classical description if I don't do interventions, if I just observe my systems, but what happens if I actually do interventions? So again, what is a classical intervention? It's to force A to assume a value that it's under my control. So it's basically saying, well, I force A to not listen to X and lambda anymore. But what would be a quantum intervention here? It would mean that like Alice, she's receiving this X variable and she's receiving part of her entangled system with Bob. And she just say, look, I'm not going to listen to you. She throw this in the trash and introduces a new mechanism. It can be a classical mechanism that forces her variable to not listen to these two other variables. So from Bob's perspective, what he doesn't know what Alice is doing, if she's doing an intervention or she's just observing her system. What Bob knows is that he has his part of the system that we have to trace out the Alice part. So for Bob, he only has like this row B. And he's receiving a classical variable from Alice that it's the outcome that she's sending to him, and he doesn't know it's an interventional outcome or it's an observational one. And he uses that to define what is the kind of measurement that he's going to perform in his system. And then is there a mismatch between this classical and quantum description, even though on the correlational level, I have a classical description? And the answer is yes. And to show that, we have to show, like one way of showing that is that we can violate the classical bounds on causality, on the average causal effect. So here I'm comparing, so we are going to see this clearly, but I'm going to compare observational data that I use to compute this lower bound with interventional data that I do interventions to compute these actual A's. And I compare what I get here from what I get there. So let's see an example of that. Let's say that the quantum state shared here between Alice and Bob, it's a Werner state, like some maximally mixed state with some maximally entangled state with some visibility V, and with the complement, like here, just the white noise. From Bob's perspective, his partial state is just the maximally mixed state. So if he's performing some projective measurements on his system, independently of what Alice is telling him to do, he's always going to observe spin up or down with the same probability of half. So it's like, it doesn't matter if Alice tells him to do his outcome, or the probability of his outcomes are always going to be the same. This means that this ACE, this average causal effect, is going to be 0 for this quantum experiment here. But now I can choose for the observational experiment that I do some measurements for Alice and Bob in such a way that this classical bound is going to give me some positive quantity, at least for some level of visibilities. So what this is telling me, it's some sort of of quantum advantage for causal influences, because something that classically needed to be positive with quantum shared correlations, it can be zero. And more than that, it's telling me that these nice bounds that Pearl has derived in the past, they are not valid anymore if quantum effects are present. And we can do that in a much more general way. So like I'm just going to tell you some general results here. First, we can prove that every pure entangled state can generate correlations that violate this classical bound on A's. And again, we are in the simplest instrumental scenario, meaning that we cannot violate any Bell inequality. We cannot violate any instrumental inequality. So from the correlational level, our experiment would look classical. So what I'm telling you is that we have a new witness now that works at the interventional level, that it's able to detect this non-classicality of our system. And we can do the same for the measurements. We can prove that every pair of incompatible rank 1 projective QB measurements can generate these non-classical correlations that violate the classical bound. So in a sense, necessary condition to violate these causal bounds, it's either to have entangled state and this pair of incompatible measurements, okay? And we can go a bit beyond and ask, okay, so if the classical bound is not valid, can we derive bounds, new bounds for the causal influence that remain valid even if quantum effects are present? And there are many different ways of doing that. Like in the paper, we do this by using some properties of Hilbert spaces and like Cauchy-Choix inequality. So it's kind of simple to get to these bounds. We don't know if they are tight or not. They are probably not tight, but shows that we can do something similar that Pearl did some years ago, also for quantum physics. In a sense, bound the effect of interventions in quantum experiments from observational data alone. And here it's an example of that, like it's some cut in the probability space. Here, just these two coordinates. Everything that it's in this blue region here that subsumes this red region as well, we would have a classical causal effect that would be higher than zero. Here, the same. In red would be the case of like quantum causal effects that are larger than zero. And in this black case here, it would be like the same, but for post-quantum theories, for non-signaling theories. And what's nice here is that we see a gap between the classical and the quantum. So if I'm in this blue region, this means that I have quantum violations of the classical bounds. And if I'm in this red region here, I have post-quantum violations of the quantum bounds. So I'm going to get back at my conclusions at this point here. Okay, and at the end, we decided to do an experiment because we said, okay, this is really a new kind of non-classicality witness. So what it...
Sorry, yes, no, I just warn you have 2 minutes and then will be time for questions. So if you can get to the conclusion. Okay, perfect.
I'm finishing.
Okay, thanks.
It's a new kind of experiment. So basically, we are doing that with entangled photons. And we have here, we are imposing, we have this setup that imposes the instrumental causal structure. And the new thing here is that in Alice's station, in Alice's measurement station, we need to have a way to decide from run to run of the experiment whether we are going to perform an intervention or to just make a usual observation. And we do that with a quantum random number generator, optical switch, depending on what happens here. Like Alice is either going to perform like the usual measurements of her, or it's going to make some intervention in her system, force her system to get an outcome. And from Bob's side, he doesn't know what's going on. And here are the experimental results. So these are two different experiments with different states and different measurements. In both cases, we see a gap between what we get by doing interventions in the experiment. This would be these green points here that are below the classical lower bound. So we have a violation of the classical bound. Here is the same. And in this plot, it's nice because we are using the quantum bound. So you see that the quantum bound for our experiment gives us non-trivial bound. So it's telling for all these blue points here that I don't need to make an intervention to know that in my quantum experiment, there is some causal effect from Alice to Bob. So I don't need to make interventions to know that. So this is like a nice quantitative tool for quantum causal model. So I come to my conclusion. The main message here is that causal structures beyond Bell, they are very rich. Even simpler causal structures can lead to new phenomena, and they remain almost unexplored yet. So like they can lead to new and stronger forms of non-classicality, can be applied to information processing. And the main message I would say is that they lead, I would say, to a new signature of non-classicality. And I mean, I think I have many open questions here, but I will focus in one. That it's the fact that we have focused in informational principles like local orthogonality, information causality, and many others. But all of those, they work at the correlational level of our experiments. What about the interventional level? And what I mean with that, can we explain this gap between post-quantum and quantum using new kinds of informational principles? I think this is a nice question for which I have no answer. And to conclude, here are the papers that I've taken pieces from, and I take the opportunity to thank all my co-authors. There are many here, so hopefully you can read them. And I also thank you for your patience and attention. So hopefully we still have time for discussions. Thanks.
Yes, thanks, Rafael. Yes, so we have still 7 minutes for questions. Valerio?
I thank you for the very clear talk. And first of all, I have to apologize that that I didn't follow your works because I was in an administrative black hole during those years. I have a question about device independence. So just listening to your talk now before, not having seen anything before, it seems to me that it's impossible to, you must fix something about the dimensions in order for the instrumental scenario to be, to give some meaningful results, right? Otherwise, it would become trivial. Is it correct or I'm wrong?
Hi, Valerio, thanks for, well, it's a very nice question. And the answer is partially no. So there are two things here that we are doing, like in the instrumental scenario. We are looking at correlations, and in this case, it's fully device independent. So what means device independence for more general causal structures beyond Bell, or at least for me? Device independence means that we are imposing a causal structure to our experiment, but we are not assuming anything about the states, about the causal relationships. I mean, they could have any dimension, they could be linear, they could be nonlinear. I don't know if I'm measuring like a projective measurements or POVMs. So it's really device independent. So the violation of an instrumental inequality is fully device independent.
Just to explain about my doubt, what prevents A from sending both its outcome and X to B, at which point B has absolutely all the information to compute whatever and then can create all kind of correlations?
Yes, so this is an assumption. Like in this sense, it's this that I'm saying. I'm imposing this causal structure to my experiment. I'm like blinding. I don't allow X to go to B. But let me say that this is not only in this case. In Bell's causal structure, we have something very similar. Okay, we can use a special relativity to say that it's really local, that Alice is not listening to Bob, but we have a causal assumption there that we cannot close. And it's the causal assumption of measurement independence. How can I really be sure that the choices of Alice and Bob, they are independent of my source? Okay, so just to say that this kind of assumptions, they are not only in this case. You can take the same for the prepare measure scenario. Like we are assuming that the choice of which button to press to prepare our state, this is not being communicated to Bob. The same is true for the information causality causal structure. We have to assume that all the information that Bob has is given by the message that Alice is sending to him. So yeah, we are forcing, we are imposing a causal structure to our experiment. And of course, there are some assumptions there, but this is not only in the instrumental case, these are for any causal structures. So just to comment that in the interventional case, I would still call this device independent, in the sense that the intervention that I'm doing, it's on a classical variable. Like I can put a black box here or in the measurement station of Alice. Like this intervention is just saying, look, whatever Alice did, I don't care. I will force my variable to assume a new value that it's under my control. So at the best, this is like we can call some sort of semi-device independent, where I don't care about states and measurements. The only level of trust I need to have, it's on this classical intervention on a classical variable. So yeah, I would say this is a device independent.
Yes, we have a question online from Gemma, and then we'll go to Carlo. Yes.
Hi, it was super nice and very clear talk. Thanks a lot. Thank you. Yeah, I like a lot.
Thanks, Gemma.
I have a bit of a crazy question. Have you thought of applying any of these, either in the classical or the quantum case, to some toy models of consciousness? In particular, like integrated information theory has some sort of very intricate causal structure. And I can imagine that if you have I don't know how many variables you can do, but I can imagine only a few. But perhaps for some toy model or something like that.
Well, yes, I don't know how to do that. Like I've read the papers that you mentioned, and this is something that clearly comes to mind when seeing all of this. I think it would be very interesting. It's like borderline whether it can be done or not. Maybe there are just too many variables, and this is an important point that like we are limited here by computational power. To derive these instrumental inequalities or to find violations, we have to use like linear programming. If you want to go like beyond this linear case and treat like more complex networks with independent sources, then we have to go to like the inflation technique, like algebraic geometry, and then I mean it becomes a nightmare. But I don't think that there is anything fundamentally difficult here. It's just like a computational power, and I think it would be very nice to apply these tools there. So let me just say something like. It's off topic, but like we use this causal framework to, for instance, analyze this famous experiment of like this delayed choice experiment, like this wave particle duality and so on. And we have very strong results there that come from this causal, from this fresh perspective on an old problem. So I'm mentioning that because I think this is a very powerful tool that allows us to reanalyze all the scenarios, but also to treat new ones. So I think it would be very interesting, but I haven't tried yet. So I would be very happy to talk about that.
And maybe can I?
So maybe I have just one quick question, and then we should wrap up because we are a bit late.
Sure.
Okay. So very fast, thank you. I didn't know anything about this quantum version of the causal model analysis. This is very interesting. I have a question about the arrow of time, which is the following. In the book of Judea Pearls, I read it with a question of what can I learn about the arrow of time, and what he's very clear in. Saying that is an input in all that. Somehow one assumes that around there is an entropy gradient, and the intervention act toward the future, not toward the past. That's an assumption. Does anything changes when you go quantum? Or how do you think about that?
Well, thanks. That's a very interesting question. And even in the classical case, I think we don't really understand the arrow of time. And I mean, and what I mean with that is like, even in Pearl's book, like he said that this is a mystery, that like why the arrow of causation coincides with the arrow of time. And I mean, I don't know what to answer to that, but there is no reason why these two things should be the same. I think it's a similar question to why the gravitational and the inertial mass turn out to be this. So, I mean, and in the quantum case, I really, I think things are even worse, because you can have like these superpositions of causal orders. And I think things are even more complicated, because now you don't have a clear direction of causal errors. Like one can be causing the other in superposition with the other way around, but still time is going forward. So, I mean, I'm not trying to answer your question, but just say that I think it's a very interesting question that I have no idea how to answer.
Okay, thanks. So let's thank Rafael again.